So coming back to our equation, we know that the amount of the final amount of ammonia should be given by the initial amount of ammonia minus the amount of ammonium that has formed using this equation. So because it's a weak base that reacts, very little amount of this one forms. It's very little amount, especially when you are dealing with maybe higher concentration of this. Very little amount of this is formed compared to what we are starting with. So what happens is that we can decide to ignore this one. We can decide to ignore this one because it's very little. It's the same. It's like 5 molar minus 0.0005 molar. That is the same as just 5 molar. So in the end, what is important is the initial concentration of ammonia in terms of calculations. This is the important concentration that we can use, especially if you are dealing with molar amounts that are 0.5 and above. Why is this important? Let's go on and see. So we say that Kb is equal to this from this equation, right? Kb is equal to ammonium OH over this. But we say that the concentration of this is equal to the concentration of this. So we can just, both of them should be given x. We can just take one, either this one, or we can take either this one or this one. So in this case, we decided to take the OH because it's important from what you will see later on. So OH squared is the same as the concentration of OH times the concentration of this. So this becomes OH squared over the concentration of ammonia is equal to Kb. So again, Kb is the concentration of OH squared minus the concentration of ammonia. We play around with this. We see that the concentration of OH squared is equal to Kb. If we multiply both sides by the ammonia, is equal to Kb and the concentration of ammonia, or OH. The concentration of OH is equal to the square root of Kb times the concentration of ammonia. What does this mean? It means you can calculate the concentration of a base if you know the Kb. That's it. If you know the Kb and the concentration of the initial amount of the base that you are using, you can calculate the concentration of the OH that base can produce in water. If you know Kb of that base and the initial concentration of that base. It's like what we did with acid. We found that H plus is given by Ka times the concentration of a weak acid. In this case, OH minus is given by Kb times the concentration of a weak base, but you put them in the square root. So coming back, POH is equal to the negative logarithm of OH. So if you put a negative log here, you also need to put a negative log here, which is equal to a negative log Kb and the concentration of the base. But another important equation that we are introducing, pH plus POH will give us 14. So if you know the POH, you can calculate the pH of the solution. In this case, pH of the solution that you know is POH should be equal to 14 minus POH. why is this information important? Let's go deal with an example. Determine the pH of 2.5 molar of CH3NH2. That is a base. Its Kb is 4.38 times 10 to the power 4. How do you solve it? It's simple. First, determine the pOH. So the pOH of this solution is negative log OH, which is equal to negative log Kb times the concentration of the base. So we know the concentration of the base as 2.5 molar. We know what our pH is. Oh, sorry. Let me get rid of this pH. So we know what our pH is. We know what our Kb is. We just plug in the numbers here and immediately we get our solution. So pOH is minus log 4.38 times 10 to the power 4, that is Kb. Yeah, this one is supposed to be to the power 4, times the 2.5, that is the concentration, which is 1.48. So the pOH of this ammonia, 2 molar of this ammonia, is 1.48. It means it has a lot of OH ions in there. But pH plus pOH is equal to 14. Therefore, pH of this solution is equal to 14 minus 1.48, which is 12.5. So immediately, if you have a pH 12.5, you know that you are dealing with a base, because the pH in that case is greater than 7. So I want you to work on this one. Use the same formula. What is the pH of 1.2 molar of C2H5NH2? That is another base whose Kb is 5.6 times 10 to the power 4. That is your exercise. Now let's talk about model 4. Addition of strong acid to a solution of a weak base. So we have a weak base and you want to add an acid to them. As with the acid, if you add a strong acid to a weak base, the strong acid will react with the weak acid, and the solution that you have will contain the conjugate acid that is of that weak base. The equivalence will occur when enough base has been added. So when there is no kind of acid is left, or there is kind of no base left, we can calculate the pH using similar means like we did with the acid. So let's just go straight to a problem or the process that we can use. So pH is given by pKa plus log CH3CH3O4. We know that for acid, but what about for base? For base, this is what we have. The Henderson-Hasselbalch equation. pOH is equal to pKb plus log NH4 NH3. What it means is, if we know the base, and its conjugate acid, we can calculate the pOH, and then we can calculate the pH of the base. That's what I'll deal with as we continue.